Hello, everyone. Good morning. Thank you to join us. My name is Kairo. I'm an open source software engineer. I'm a maintainer of TUF, the update framework, also in-toto. And I'm here today with Marina.
Yeah, hi everyone. I'm Marina. I'm a research scientist at Edera, and also one of the co-chairs of CNCF's tag security, and most important for today, a maintainer of the TUF project. So we'll talk to you today about TUF and how to toughen up your software supply chain, as the title says. So first I'm going to talk for a minute about this software supply chain metadata that a lot of folks have, and I guess the problem that a lot of folks have. So you have an image that you want to distribute to users. You know, you probably already have a pipeline for doing this. You have a whole process. And then you have all this other stuff, right, that you're starting to generate and look at as part of your software supply chain. I think SBOMs, probably the most famous of these, also attestations, maybe VEX to go alongside those SBOMs, and policy, kind of all this other information about the image and its dependencies and its vulnerabilities that you want to also distribute alongside the image. So you have this whole collection of things that you want to somehow get to the software consumer while making sure that none of it is tampered with, so that they actually get not only the image they expect, but all the other metadata and stuff that they expect. So we're going to kind of talk about this problem very generally and then go back to this problem of software supply chain metadata distribution. So first we'll just look at how this looks a lot like the original distribution problem. How do you get that image to users securely? But you can really distribute anything securely in this way. So what can go wrong? Why do we need to have this whole talk about secure software distribution? You just take your software, you're the software producer, you take this software foo and you send it to the consumer. What could possibly go wrong? I'm about to tell you. So the first thing that could go wrong is that an attacker could just replace your software with malware, right? Like they could just replace it with anything they want, and then your consumer would be very sad. I should have put a frowny face there because they're getting the wrong software. Another thing that can go wrong is that they just get the wrong version of the software. And this is a slightly more subtle attack that I think a lot of other protections have more trouble with, right? Is that you once had this version of the software, foo 2.2, and this was the correct version. It was great. You signed it. And then maybe there's new features that are added. Maybe you've even patched some security vulnerabilities. And now you're on foo 2.3. But you want to make sure that the consumer is actually getting the correct version and not this old version that you no longer want to be distributing. So what about signatures? I hinted at this a second ago, but let's just sign the software, right? Why can't we just sign the software and then make sure that the user gets the correct version? So the first problem here is with this out-of-date metadata, right? So you have foo 2.2 was valid, right? You signed it with your proper key, and it was correct. And then when you produced foo 2.3, you also signed it, but the consumer doesn't know any better, right? If an attacker is able to give them foo 2.2 with that valid signature, they'll still think that it's valid. The other thing that can go wrong, depending on how you're doing signature verification, is that the attacker can also use public key cryptography, right? They can take some malicious package and sign it with some arbitrary key, and that is a signed package, right? So there's like this extra step where it not only has to be signed, we have to make sure it's signed by the correct person. And the correct person today, right? Similar to that previous problem. So yeah, you now have a key distribution problem where you need to make sure that the software producer, not only do you have this package securely distributed to the consumer, you also have the key that you need to use to verify the package. Pretty soon you're using keys to sign keys, and where do we go from here? Okay,
yeah. What we talk about here, it's quite complex. So for that, I create a call service. That is, you can have your personalized bovine voice. And we use that to create examples, real examples, about using the update framework here. So what is this service? It's a really normal service with one API that the user can request the custom bovine voice, and it is store some data in a storage, and they can get it back. And as this service is quite critical, we need to secure that, right? So let's see how. By the way, it's so critical that, of course, we use Kubernetes, right?
Yeah, so now we have our critical service that we're securing with and distributing securely with TUF. So now let's get to what does all have to do with this update framework thing that's in the title of the talk. So what is TUF? TUF is a framework for secure software distribution and updating that's designed to protect the freshness, and consistency, and integrity of software being distributed. It does this through a number of means, and I'll go into more details about how it works in a sec, but it uses this principle of compromise resilience, so that even if something in the system goes wrong, the system remains secure, right? It takes like a cascading series of failures to actually deliver the wrong software to people. So yeah, this includes repositories, keys, developer accounts, anything like that. Only one of these being compromised is insufficient to actually do an attack. This allows us to both reduce the impact of a compromise, right? No one compromise is enough, and also allow for secure recovery when those compromises do occur. So I'm going to walk through kind of how this works in TUF. So first we have content integrity. So how do we do that? So you have this package. This is the one we're going to distribute in this example today. As I mentioned earlier, the first kind of thought folks have is, let's sign the package, right? So we have a signature on the package. There's some downsides to just signing it in the package like this. Primarily, it's that once you sign a package, right, if you put the signature inside the package, that actually changes the hash of the package. So if you have multiple signatures or anything like that, it gets really awkward to kind of unpack those. So what we're going to do instead is do what we call a detached signature, which is basically you have the file and then you have another file, what we call a metadata file. In this case, it's in JSON in this example, which includes the signed hash of the file that we're distributing. And of course, you have to sign that too, right? So now we have a signed secure hash of the file. But how do we know what key is supposed to be used to sign this file? So now let's put that key in another metadata file and sign that. You might notice this is going to become a problem pretty soon, right? Let's just do this just one more time to what we're going to call the root.json. This is our root of trust. And because it's our root of trust, we're going to do what we call multi-signature trust. So this key at the top, the unlabeled key, is actually multiple keys, right? So you can have multiple keys. These can be your most secured keys, probably hardware tokens, owned by different people, maybe even on different continents, right? You can do all kinds of crazy stuff to secure this, because it's going to, as you're going to see, this file actually changes way less often than the other ones, so these keys can be used less often. That's kind of why we did these 3 layers here, is that the keys that are used more often can be more easily revoked, right, by more secure rules. Okay, so now we're signing the file, but we still haven't dealt with this problem of old versions, right? So what happens if we now release foo 2.0, right? We want to make sure that folks are using this foo 2.0 instead of foo 1.0. So we add the hash of foo 2.0 to this foo.json, re-sign it with the key A. But right, if you had the old foo.json, it might still look valid to some of the internet, right? If you're just able to replay that old metadata. So to prevent this, we put version numbers on these metadata files. Foo is on v2 because we just changed it. And you put these version numbers in another file that we're going to call snapshot, and you sign that. And you also put that key in this root, this really secured root location, right? So this is where you're finding your initial keys. So as the versions update, the snapshot is going to update pretty frequently, right? Every time you have a new version of something, the snapshot will update, be re-signed, but no changes have to be made to root, right? So you can still keep those root keys offline and less used, and able to recover if this more used snapshot key, if something goes wrong with it. You can, of course, still replay a snapshot file, right? So we had a previously signed file that said foo was on v1. How do we make sure you don't use that? It's not a timestamp. Same idea. Put it in metadata, sign it, and that includes the current snapshot along with a timestamp. And then depending on your configuration, you can set a window of time, right, within which this timestamp needs to be valid. It's basically a heartbeat, I think is another way that these can be referred to. And the idea is that because this heartbeat is very small, right, it's just a hash of the snapshot and a current timestamp, it's very efficient to just re-sign it, redistribute it, and so you can make sure that everyone's getting the correct versions of the package with pretty low overhead. And that gives what we're going to call freshness to the repository. So now that we kind of have hopefully a brief understanding of how TUF works, how these different pieces fit together, let's go back to the problem that we're solving. So we have a package. In this case, we're going to talk about Nginx, give it a real name. And then you want to make sure certain things happen before it goes into a production environment. So you want to make sure that this package that you're ingesting as part of your software supply chain is a good package before you then send it off to your production users. You might want to make sure that it has an SBOM. You might want to look at this SBOM for CV, or maybe the package itself for any CVEs, maybe do some security scan, maybe check the signatures from other systems that you don't control, that maybe aren't using something as fancy as this. But you can still make sure that they're valid and that you've done all those verification steps. So once you've done all those requirements, you can kind of internally set up a TUF repository that you control and manage. So after these requirements are checked, you can ingest the image to your TUF repository before it goes to the production environment. Yeah, so you check the requirements, add the image, and then only then, if it verifies from the TUF repository, does it end up being installed in a production environment. This means that you don't have to wait for any upstream open source repositories to do all this verification. You can do it yourself. And you're also not trusting every package on every open source repository, right, which maybe not all of them are as good as others. So this kind of lets you ensure you know what you're downloading into your production environment. So to summarize, what does this give us? This gives us verification that checks have been run, because somebody with a signature is basically attesting, you could say, that those checks have been run. It gives you control over ingested images. You're not relying on some upstream repositories checks. You control which images are securely ingested, not just because they're signed, but because you signed them. And this also allows you for secure recovery after CVEs are discovered. As we discussed previously, you can, if you update TUF metadata, the users will know right away that it was updated. So if you remove an image from your TUF repository, your internal TUF repository, you can know that within some period of time, no one in your production environment will be using them. And this also gives you a single root of trust for your, a single root of trust with strong protections for your images that you're using, right? So you have this one root of trust, that root role in TUF, and then that can give you all the different packages that you're using. So what does this look like in practice? So this is kind of a lot of theory so far, right? So you have what is the TUF project in the CNCF? So the main thing it is a specification that kind of explains what all those rules are, how they work, how to make sure you use them securely. It also includes a bunch of different implementations in various different programming languages for folks who want to get started on this and actually use it in practice. Languages that include Python, Go, Rust, PHP. I think there's a Java one too. I didn't put that logo up here. As well as a bunch of different deployments in all kinds of critical services, including the most important critical service.
Yeah, including call service. So we use TUF, of course. We're trying to do the right way. So how call service use TUF? Because we saw the explanation, a beautiful explanation from Marina, but TUF is TUF, right? So in that case here, we are using one of these implementations that is our stuff, the repository says for TUF. You can deploy it to use containers. Helm charts are available for you to demonstration or production deployment. And we explain how we organize all this TUF metadata that we mentioned before. So what you're going to see here that we have those targets, the metadata, actually the delegations, we have a first set here is for the provenance, the way that we can store the SBOMs, attestations, and also our artifacts that we use to build our service. And also the content that we generate to the user, we also we have one metadata that we can store it. Then the user can download their bovine message in a secure way. So, and of course, we want to secure our third part. As we mentioned before, Nginx in the example, we use Nginx here. That is our most critical part here, because if someone gets access to that, for example, they could just give our users a bad message, and we don't want it. So we in that I will show here how we secure the in-toto attestations and SBOMs. Basically, everything is stored in the GitHub releases for now, and we can use our stuff client as well, but we can use one of the implementations to download this artifact. So it means that no one could compromise our attestations here. So let's see how could be one attack. Imagine that someone get access in an vulnerability or bad administration in our site, and someone get access to our GitHub release space, and he can have rights to edit it. So imagine that attacker gained this access to the GitHub releases, and he is able to go and replace our attestation for the build, for example, by a malicious one. So how we can secure our users. So using TUF here to download this attestation, it will tell that we don't trust in that attestation. But if you just use like a wget to download it because it's available, you can get the malicious attestation. Well, yeah, with TUF, without TUF. So, but we also want to secure our container image, like the critical dependence that we have for our deployment. Let's show this because this is more interesting, I would say. So we see that we have the version 1.25.5 of Nginx, and we want to update it to the next version. But imagine that we need to go through some process in our organization. If the licenses are okay, CVs are okay, everything there. If someone try to deploy it, he's not allowed to deploy it. He's not allowed to pull this image. So to do this, actually, we need to add this artifact to our TUF metadata. So we did it. But still, if someone just add it to our metadata, someone cannot deploy it because it requires some trusted signature. So, okay, we did our verifications, license CVs, everything. Now we sign it. We say, okay, let's add to the TUF metadata, and I use my SIG store to sign, for example. And now, after the signature, if we try to deploy this authorized version in our environment, we can do it, as you can see right now. But let's say that the 1.25.5 is malicious, and you don't want that we do some regression here. For some reason, someone submit a new PR changing that. We don't want that. So let's delete that version. But also, you cannot just attack by deleting it from the metadata. It requires also, again, a signature. So we need someone to sign it. I think now it's Marina that's signing. Yeah. So now we are allowed to go and allowed to not download it. Basically, now our deployment doesn't trust anymore in that version. So to get involved to the project, yeah, we have the TUF documentation, the RStuff project. TUF is more the specification, but in that repository you can also find implementations from Python TUF, Go TUF, and others. The RStuff is a project under OpenSSF, and it allows you to not deal with all the implementation of TUF repository. That's quite complex. You can reach out to us to the TUF in the CNCF Slack, and also in the OpenSSF in the RStuff. And you can find different implementations and more here. Yeah. So yeah, I think Kairo about covered it. So yeah, thank you all so much for coming. I think we have a little bit of time for questions. So. Looks like there's a floating mic here if anyone has questions. So.
Yeah, many thanks for the introduction. One question. So currently most people, definitely us, deploying stuff in Kubernetes using some GitOps approach, using Flux or Argo CD, something like that, so not the TUF client. So is there any discussion ongoing how to bring both worlds together?
Sorry, can you repeat about the client you mentioned?
Yeah, so I mean, this verification with the TUF client was really interesting, of course, but currently people use, as I said, Argo CD or Flux to deploy dynamically to Kubernetes, and the verification is maybe done, so Sigstore signatures with Kyverno or some other tooling. So all these tools, as far as I know, don't support TUF now. And the question is how this cool metadata validation could also be done with maybe potentially other tooling.
Yeah, it could be implemented in your, for example, in your pipelines as well. Or of course, because you can use those TUF libraries to build your own, let's say, client. We have been working in like generic clients that you could just configure and use. And of course, like right before this presentation here, I was trying to change the code from the Docker client to just implement, for example, GoTUF there, that you could use a parameter to verify a certain TUF repository before signing. But the idea of the TUF client is more for depends a lot of, it's really difficult to create a generic and a trusted client. That's why you need to use the libraries mostly to build your.
Yeah, I think I'd add that the stuff that's internal to the company can happen before it goes to your final deployment pipeline, right? So one easy way to do it before that support is fully integrated is just to do verification one step before you send it out to Argo and stuff, which isn't quite as satisfying, but can be done faster. But yeah, we're definitely actively working with projects like that to help make this all more built in. So.
Many thanks.
Hi, thank you for the talk. From a developer experience or kind of way, so usually developers have maybe their pipeline somehow checked in as code, maybe an Azure pipeline or Go Actions, stuff like that. GitHub Actions, sorry. How you make sure, like, is this the part where you will usually do the signing, or is there like a separate part where, let's say, a clumsy developer doesn't like misconfigure it and then ship only partially signed, or like doesn't include the right stuff for the signing? Do you have like a separate step for that, or how do you usually do that?
So the question is how to make sure that you don't forget to sign it before you try and send it out to people?
Yeah, and that the important stuff is signed.
Yeah, I think, well, I'll let Kairo answer too, but I think one idea is basically just to you do the verification at multiple points, right? So once they do it, you try to do the TUF verification, and of course if it fails, that means you can kind of send it back to the developers, and you can put this all in the GitHub Actions, right? And say, try again, please run these commands or whatever before you send it out.
Yeah, so like one thing where I was wondering how it could play together is, I mean, the SBOM stuff is easy to generate, but when it comes maybe to something like static code analysis, and you want to make sure maybe that there's a proper report for the static code analysis, let's say SonarQube or something like that. Yeah. Is there something, like, obviously every project has its own configuration there, and like any recommendations how to configure that or how to handle that?
I would actually say that probably the thing I would look at here is TUF's sister project, which Kairo can talk about too, about in-toto. Because in-toto, I think, has a more generic format for attestations, right? It's not just signatures on the files themselves. You can actually put some kind of rich data inside of the attestation, right? Which can say, for example, this was the actual outcome of the scan. This is all the stuff that happened. These are the inputs, the outputs. And then have that be signed. You can also distribute that alongside the TUF. There's ways to connect the two. But I think that signature format might be a better fit for that.
Thank you.
Yeah, and with in-toto attestations, you can also create policies to verify that. And for example, combining with TUF, if some policy doesn't pass because there is not enough coverage, for example, you could not allowing this to be signed. And you could, for example, also sign the TUF metadata using let's say, machine keys, like KMS keys. So one of your first signatures could come from your pipeline that said, oh, everything was good, so you sign that. And if you sign that in a specific delegation, let's say staging delegation, you could still use this to deploy, even you verifying if it's checked for your next test level. And when you say, now I want to release, you could have it in another delegation and say, now I want my release manager, my lead sign that with their SIG or their personal keys, then we can release it.
Thanks a lot for all that clarification around the project. I have a question around your boundaries in the framework and what you propose. Does it something what overlaps with SLSA, or it's something combining with SLSA? Where is the limit? It's not completely clear for me.
Yeah, so the SLSA framework, it's actually, it's related to the in-toto framework. I think they use a similar attestation format. That provides, I think, it really focuses on, I think, the build provenance situation in this process, right? So it focuses on saying, these are the actors that were supposed to do the builds, this is what happened. But at the end of that kind of salsa framework, you have, well, I guess in the middle, between when you create it and when you verify it, you have some, you've got this set of attestations that you created, this salsa attestations, you have the image that you need to distribute, and you can actually then securely distribute those things with TUF and make sure that the salsa attestations themselves are also up to date. Right, so it wasn't just that, like, this version of the software was built correctly, it has the SALT attestations, it is this version of the software. When you do that a second time, you want to make sure that people are getting the new one, right? And so you can use TUF for that like distribution of the supply chain metadata step.
Okay, you provide the packaging finally of everything.
Yeah. And there's a couple of existing integrations of mostly in-toto and TUF, but in-toto and Salsa, again, they kind of do a similar attestation thing, so you could like very easily do the same thing there.
I was wondering about the repository service. Is this a requirement, or is it also replaceable with, for example, a generic OCI registry to keep the metadata?
I will explain a little bit with our stuff. So our stuff, or TUF in general, doesn't care where the artifacts are stored. You can use OCIs, you can use S3 buckets and everything else. The TUF metadata usually doesn't go together, but it can even be together with your artifacts. And for example, our stuff right now supports PVC volumes that you can share later, and also S3 buckets. So you can have, and we could, for example, easily, if required, in the future, have OCI support for the TUF metadata in our stuff as well. So.
And maybe if I may ask another question, to continue on what somebody else asked, is there a plan to maybe have an admission controller for TUF to run it in Kubernetes and then deny admission when?
I would love to see it. If someone wants to join me, I'd love to do this. Okay. Yeah. It's not that hard, but I'm not the expert in Kubernetes, so.
All right, I think we're just about out of time. So thank you all for coming, and we'll be around here, and we have a kiosk also in the project pavilion if you want to come ask some more questions. Thank you all.